Okay, so welcome to the stream. This is my weekly coding live stream where I work on my Sudoku Solver. And the main goal for this week is to work on performance. So I did work on performance last week. And the results from last week were we started with 31 minutes baseline runtime for our big benchmark database. So that's 9 million Sudokus. Managed to get it down to 22 minutes after the first day, and after the second day we were at 17 minutes. So honestly, those were mainly just like optimizing the code itself. I didn't really do anything specific to this solver at all. So very generic optimizations. And this weekend I really want to work on something that's actually more related to how the solver actually works. So in particular, and I also want to finally fix the building issues, which will not be easy, but well, we will see. So if I go to the solver, basically our solver works in this big loop. And this is kind of to simulate like how a person would solve a Sudoku. So actually, I think the music is a little bit too loud. Let me just get it a little bit quieter. Okay. So we kind of go from the easiest solving techniques and then ramp up. So as long as we can apply the easy stuff, we just do the easy stuff. And the moment the easy stuff isn't good enough, we just go to the next level, essentially, right? So if you look at this code, it's basically we grab what has changed in the puzzle, which is kind of what we use to figure out if a particular technique did actually make any changes to the puzzle. So here we are trying to solve groups of one. If that didn't do anything, so this is always the if has changed. If that didn't do anything, we just go to the next thing, trying blocks of size 2. Again, if that didn't do anything, then we go to block intersections. If that didn't do anything, then we try blocks of size 3. If that didn't do anything, we try to solve fish of size 2, which is X-wing. If that didn't do anything, then groups of size 4, fish of size 3, finned fish of size 2, finned fish of size 3, fish of size 4, 5, 6, 7, and then finned fish 4, 5, 6, 7. Now, the problem with this big loop is we kind of trigger these techniques in cases where they basically do nothing. And for most of these techniques, we kind of know what actually they would do. So I mean, I guess let's just take this one for example, right? Wait, what's wrong with my shortcuts? Go to declaration or usages. Okay. I guess because it's failing to compile the... Okay, let me first fix the compilation because this is annoying. Okay, configure, generate, make. Okay. Right. And I really need to figure out like what is the problem with this because I really am not sure about this warning. Right. So now if I do reload, Okay, now things should be working again, I hope. Yes, okay, right. So basically what we do here is we try to find a number, or I guess a group of numbers of the given size that satisfy this condition. And the condition for the hidden groups is basically let's just go here. Yes, so if x possibilities only appear in x squares. So let's go back to our Sudoku. Yeah, right. So if we have a situation where, let's say for these, we have 1, 2, 3, 4, 5, and here we have also 6, 7, 8. Let's just remove the 1 so it fits. Okay. So if we would have this kind of situation, then for these 3 squares, 6, 7, 8 can only appear in these 3 squares in this row. Inherently, that means that the 2, 3, 4, 5 are not possibilities in these squares, because if I would place, 2 here, well then suddenly I have 2 squares where I need to fit the 6, 7, 8, and that doesn't work, obviously, because those are 3 numbers. So then what I can do is I can remove the 3, 4, 5 from here, and I have, slightly better situation. Now, if we think about like when do we actually want to do this search? For a given row, is it enough that any of the squares changed for us to trigger this search? It might be. Trying to think if there is a better way to not run this every time that anything changes in a row or a column or a square. So I mean, we can do slightly better. So or can we? So what complicates the things is, it doesn't have to be neat like this. The situation can also be something like this. And this still works. So if I had like the 2, 4, 3, 5 here, the correct operation to do is to remove the 2, 3, 4, 5 from here, because 6, 7, 6, 8, and 7, 8 makes 3 different numbers. And those only appear in 3 cells, so inherently those 3 cells have to be those numbers. So I cannot really do anything with like the number of possibilities in a square, because like that could be anything really. Can I do... I guess I can ignore if a square changes to like a solid. Oops, no, not like that. So if I change a square to like a set number, so like 1, right? Then that obviously will not be member of a hidden group. That's not super helpful, but it is something. But otherwise, I think like for hidden groups, I kind of need to run it for every case, I think. Okay, so let's just write this down. So hidden groups, for hidden groups, we must trigger on every square change. Okay, what about naked groups? So naked groups are kind of inverse of this. Yeah, here. So if we pick x squares and the number of possibilities within these squares is x, then we can remove those from the other squares. So if I just draw it here, so let's do undo, right? Let's get rid of this. So if I would have, in this case, 6, oh damn it, I would center, right? So 6, 7, 8. Oh, that's a little bit too much. Okay, something like this. So if I have this situation, well, then I have 3 squares that only have these 3 possibilities. So obviously one of these has to be a 1, one of these has to be a 6, one of these has to be a 7. Because if I don't do that, then like it breaks, because I run out of spaces or run out of, you know, numbers to put into these squares. Well, what that means is 1, 6, 7 cannot appear anywhere else in this row. So then if I just grab this, then I can just okay, then I can just remove the 1, 6, 7 from here. So when do we want to trigger this one? Yeah, I think like this one we also might need to trigger on every change. Like I don't really see. There is a slight optimization here. So for these, we definitely know that. So make it groups. We don't have to trigger on every square change. We trigger on a square change where the number of possibilities is less than equal than the size of the set, right? Because, okay, so let's say this was the situation, right? Like if I remove the 6 here and I'm looking for groups of size 3, well, I don't have to trigger the search because like this already has 4 possibilities, so it's impossible to be part of a group of size 3 with 4 possibilities. So yes, we can do slightly better like that. That's, I don't know how useful of an optimization that will be, but it is something. Okay, let's think about the block intersections. So these are situations where, let's say we have a row 2, 3, 4, and then we have a number that's only in the intersection with another block. So in this row, we are saying 1 can only be here, and let's say this here was like 1, 2, 3, 4, 5, 6, something, something. So if we know that the 1 has to be here in this intersection, then obviously these ones are impossible. Because if we would place a 1 here, well, then that removes the 1 from here, and suddenly the row 1 has no 1, like we just completely screwed up everything. So in this case, what we can do, we can just remove these ones. Okay, so this one, when do we want to trigger this one? This one, okay, so this one we only want to trigger if something changed in the intersection, right? No, that's not correct. Because if we go from this state to this state, then we actually want to trigger it. So we actually don't care if something changes in the intersection. What we care about is when something changes outside of the intersection. Okay, so that's one observation. The second observation I'm thinking about is we only care. I mean, this might not help us, honestly, but we really only care about this rule if the number of instances of the particular number we are looking at is lower or equal the size of the intersection. But I don't know if we can actually do that faster than just running this rule. That's the tricky part. Because I mean, obviously, if we have this situation, then we have 4 ones in here, so obviously this rule will not trigger. So we can just skip over like trying to figure out, like basically looking at these 6 squares, we can just not look at them at that point. This might help for like a classic Sudoku, but if we have like a jigsaw Sudoku where the sizes of the intersections are like different, I'm not sure. Not quite sure about this, but it is an observation for sure. So for block intersection, so we only care if the frequency of a number is lower or equal to size of intersection. Again, still no idea if that actually would help with performance, but I mean, yeah, again, it's a thing. Is there anything else? So I really don't care about what happens here, right? I want to trigger this if something changed outside of the intersection. But again, I'm not sure if that helps, because like the expensive part here is kind of figuring out the intersection and then like checking what's in the intersection. So I'm not quite sure if these actually help with the performance. But we can write it down. So only trigger when something changed outside of the intersection. Any other observations here? Oh, I guess let me quickly have a look how we actually do this. Solve intersection, right? Yeah, okay, so there's a possibility to optimize here. We try this for, like when we trigger this rule, we try it for every number. So irrespective of the state of the puzzle, we try it for 1, for 2, for 3, and so on. But that's wasteful because, like, obviously if we already have like a set number here, oops, if we have a 1 here, well then we don't even have to look at the 1, obviously. So we can just straight up skip numbers that are already set. And I think that works even if it was here. Not that, this, okay. So even if it was here, I think it still works, because then like this one inherently removes all the ones from this block, so that's fine. So yes, we only want to let me actually slightly decrease this font because this is kind of hard to read. Okay, we only trigger on numbers that are not set. And yeah, I think that actually might give us some performance benefit. It's like we need to figure out which numbers are set in a block, but I think that should be a fairly easy operation to do, and then just go over those that are not set. Okay. Anything else for the block intersection? Yeah, I think that's kind of it. So, okay, what next? Next we have the fishes, right? So, this gets very tricky. So, let's think about it. Like basically, when do we go from a situation where something becomes a fish? Sorry, when something isn't a fish yet to it becoming a fish. So let's imagine this kind of situation, right? So let's say we had, okay, this kind of thing. Well, this still doesn't exactly work because, okay, like this. So this thing is kind of basically has a potential becoming a fish, right? So if I look at these, basically like this, right? So this is almost a fish. It has this extra 5 here. If this 5 wasn't here, then it becomes a fish with these 4 squares, and then we can remove these 2 5s. The same kind of applies to these 2 rows. Like this extra 5 is kind of blocking us from making this a fish. So that would be a fish over these 5s, removing these 2 5s. So we kind of want to trigger the fish search basically. The potential fish has to have a row that has lost like an instance of the number we are looking at. So basically, if you go from this to this, at that point this row becomes interesting, and we kind of want to like look at the other rows and try to figure out like, okay, what can we pair it with. Which is interesting because that's pretty different from how we actually do it right now. Like right now we just create like sets of rows and try to find like a group of rows or columns that kind of, you know, satisfies the frequency of a number. So we would kind of have to change this, as in we would kind of have a pivot row or a column. And try to build it up from there. Yeah, this is becoming interesting. Could I rewrite the... I'm trying to think if I can rewrite the algorithm so that I can basically give it a set of rows that had the specific number I'm looking at removed from the last pass of the algorithm. I can make it in an easy way. I can basically say, hey, like whatever set you are making, it has to have one of these rows. That's one way to do it. There might be a more efficient way to just have the set building work in a different way, as in we could have the set building start from the pivot rows and try to build up from them. But then I guess we would have to change the way our like set search works. Okay. Now I think I would, for now, let's just do it that I give it the list of rows or columns that need to be part of this. Okay, so let's go back to here. So fish rules. So for fish rules, the fish must contain row or column that had the number we are looking at removed. Okay, and then maybe we can do better for the hidden groups and naked groups. I will need to come back to that. But then the last thing we've implemented is the finned fishes. And okay, so let's just draw a thing. So if we had this kind of situation, so this is a finned X-wing. What this kind of does is we have these two rows, and let me just color this because this is getting complicated, right? So these two rows don't make an X-wing because there's this extra 5 here that kind of breaks the entire thing, right? But if you think about it, well, either this is an X-wing, so you know, the 5 in this row is one of these two 5s, or it's this 5 and this X-wing is invalid. Well, if it is an X-wing, this 5 gets removed, well, because it's on the column of the X-wing, so it would be removed. If it's this 5, well then obviously this 5 also gets removed. So what the finned fishes kind of do is it's not really a fish because it doesn't really remove all the columns. It like very specifically just interacts with one block where you have this kind of situation where it's almost a fish, but the thing that's kind of the extension, the fin, it's also removing the same value that the fish would remove. So when do we end up in this situation? When do we go from a situation where this is not a finned fish and it becomes a finned fish? Whew. Well, geez, I don't know. I think it's the same as for the fishes, right? Like if, let's say I went from this kind of situation to this situation, then suddenly we have a finned fish because like before this, like this is like, even if I remove this 5, these still don't make an X-wing because there's an extra 5 here. So I guess it needs to be over the rows that have lost the number somehow. And like if we just rotate it by 90 degrees, the same applies to columns, but yeah, I kind of think it's the same as for fishes. Like I don't really see a difference here. At least I hope I don't. Okay. let's just go with that for now. And okay. So let's go back to the groups, because I kind of want to think about another thing. So for the hidden groups, like if I have the situation like 2, 3, 4, and then 5, 6, 7, oops. Damn it. What am I doing? 5, 6, 7. When do we suddenly... When does this become a hidden group? Well, it only becomes a hidden group if we have removed 5, 6, or 7 from the other squares. Because if we didn't, it already was a hidden group and it would have happened in the previous round, right? So basically it's like going from this to this. Does that help? I don't know. The kind of issue with this is like for the hidden groups, we don't really look at specific numbers. If I go back to the code, for the hidden groups, oops, we do the number find, right? And the number find is okay. Yeah, we just union yeah, we're basically just creating groups of numbers. But we could skip over... Okay, we could optimize this thing. Yeah, we could have an early return here. So we are creating a set of numbers. And then we basically check if that set is a hidden group somehow in this block. So it's basically, you know, looking at this row, we would try, oh, it's like 1, 2, 4 a hidden group in this row, or not. Well, and we do that basically for like every combination of numbers. Well, the tricky part here is we can just straight up skip over numbers that were not removed since the previous loop, because we know that for a group to, like a hidden group to suddenly appear in this block, we had to remove that number from the block. So again, it's like going from this situation where 5, 6, 7 is not a hidden group to this situation, oops. Oh, I keep screwing up. To this, no. Okay, from this situation to this situation, where suddenly the 5, 6, 7 is a hidden group because we removed like one place where to put it. Yeah, okay, so that's definitely an optimization we can do. So hidden groups. Yes, we need to trigger on every square change, but we can filter. We only care about the numbers that were actually removed. Okay. And I think consequently the similar logic will apply to the naked groups. So when do we go by the number of possibilities. Yeah, okay, so if we have this kind of situation, how did we get here? So well, we got here because we removed something from these three squares. That's the only way, right? So there was at least one of these squares had something in them, and we removed it, and suddenly these three squares became a naked group. So actually we only care about sets that have at least one of the changed squares, because one of these three squares had to change for this to suddenly become a naked group. Yes. Yes, we still want to trigger on a square change where the number of possibilities is lower than size, but also the set has to contain at least one changed square. Okay. Block intersection. Yeah, I think that one we did correctly. Okay, so let's start doing this then. I think some of these will not be easy to implement, and I'm actually not sure if they will help performance-wise. Well, so the thing is, some of these are kind of like, we don't really need to optimize like the fin fish, for example, because this is such a rare rule that it's not too important to actually optimize it. The thing we really need to optimize are basically the first three. So the hidden groups, the naked groups, and the block intersections. Those are the most important to optimize for us. And actually, let's just go back to this thing. Oops. Oh wait, I need to pull the latest version. What the heck? Okay, let's just get rid of this. Okay, yeah. So if we run we want to run on data set, and let's do first 100,000. Okay. So yeah, I mean, but actually looking at it, like the Fint variants actually trigger more than the basic fishes, which is interesting. Kind of makes sense for Fint X-Wing to trigger a lot because that's kind of a common shape, I guess. But okay, let's just do perf report. So this was the reason I was actually running this. Shoot. Okay. Yeah, okay. I need to run it slightly differently. Oh, this, okay. I've already forgotten these commands from the last time. Okay. Want this, and then we want this command. Oh, am I running it for the first million? Oh, okay. No, this will take way too long. Let's just run it on the first 100,000. We don't need a complete profile for now. Okay. So now we should get call graphs. Right. So just looking at it, we do spend a lot of time in the naked and hidden groups. We are spending a reasonable amount of time in solving fishes. And do I see the Fint fish somewhere? Yeah, it's down here, 9%. Yeah, so maybe it will actually make sense to, solving intersections is surprisingly cheap actually. But yeah, maybe it will actually make sense to optimize all of them. But we definitely want to start with these two because these two are just insanely high. Like these are 27% and 23%. Like if you manage to optimize them even by if you manage to cut down the cases where we actually look through the data to half the time, which I kind of think this will be a much better improvement. Just if we only trigger on the things that actually changed, this should be a much bigger win. Well then, these two should just improve the performance drastically because they're a big chunk of the entire profile. Right, so how do we do this? That's the interesting question. Well, so right now how the code works is basically in the square we basically keep the original value of the square, and we have two methods. Where are they? Yes, we have has changed, which just basically compares if the original value is different from the current value, and then reset change, which just overrides the original value with the current value, and then you start tracking the state from there. So we actually might want to move this out of the square, thinking about it, because for many of these things I kind of want to get an overview that's basically a blocked based in a slightly different way, and it's kind of awkward to get this always out of the square. And I guess moreover, what I actually really care about is what happened since the last time I have tried this rule. And to do that, we kind of need to keep a copy of the state for each of the rules. Because we might be like in a tight loop doing just the, you know, hidden or naked groups over and over, and that could be improving the state of the puzzle. But then when we hit a situation where suddenly we actually need to go to like try to find a fish, well, at that point we want to not look at like what's the, you know, last little diff that happened to the puzzle. We actually want to see, oh, what did change since the last time we tried the fish? And we want to look over the data. So we definitely want to keep a copy of the state for each of the rules. Yes. So then this becomes completely pointless, because what I actually want to do is on my Sudoku, I basically want to have a, right now our copy and assignment, these are all deleted. So what I actually want to do is just make a copy of the puzzle. The reason these are deleted is actually, okay. So, okay, if you haven't watched the previous sessions, basically the reason why I'm deleting this is because we actually have this kind of tight setup where I have the data and then I have these block checkers, and the block checkers actually what they do internally, it's a little bit hidden, but here it is. They internally have pointers to the squares. So what they do is they actually point inside of the vector of our data. So if you would make a copy, we kind of need to rebuild all of this stuff from scratch, basically. But I don't actually need this. I don't actually need the complexity of the entire Sudoku puzzle. Like, I kind of need I almost need like a state dump thing, where I have a Sudoku state thingy that I can just put to the side, and then with that I can basically ask the modified Sudoku puzzle, oh, like give me the modified rows or modified squares or something, based on this stored state that I have on the side. Because for the state itself, we really don't care about the blocks and things, because the puzzle itself still has that setup. So the puzzle knows that a particle square belongs to a particle block. That doesn't change over time. What we really just care about is the state itself. Yes, that actually might be good thing to do. So let's make that. We basically want oopsie. Okay. We basically want to just have a state dump. I mean, honestly, that's just a vector of squares. I mean, this would kind of be the thing, right? There isn't really more to it. It's just the data out of the puzzle. Yeah, I think we should just do this. Okay. I don't really need to like devise new data types for this or anything. So basically what we need is std vector square state, and this will, right. I guess this is actually a good opportunity to optimize this piece of code. So far we actually do have a two-dimensional array of the squares. But that's honestly kind of silly because like we anyway return the Sudoku row here. Yeah, okay, let's just, as a first step, let's just try to get rid of this. So let's just make this one-dimensional array. Then in here, when I'm constructing this, I'm still just getting a pointer to a square and the length. That's fine. That also works on a single vector, because previously this was actually pointing to the like inside vector, but now I'm doing the same. It's just in a different data structure, so that I don't have to change. And I guess this is the same thing, so I actually don't have to change this. That's cool. That was a unintended foresight, but I will take it. So then in here, this is basically where I need to make the change. So this will not be index anymore. This will be index times size. And actually this will be slightly different. So this will be data.data. So this gives us pointer to Sudoku squares. And what I want to do is add index times size to it. So if we get index 0, we just get a pointer to the beginning of the array, and that's the first row, and then if we get like more rows, then it just gets offset by size times index. Yep, this should be the same here. Index times size. Is that it? I guess so. Let's try. Where do we actually use these? I wonder. I just want to run the test that actually is utilizing this. Okay, yeah, so it's the Sudoku main. Okay, let's do this one. Yes, okay. We need to change our Sudoku puzzle constructors indeed. So this will be size times size of Sudoku square. Yeah, okay, I think this will force a couple more changes. Data move data, that's fine. Right, okay, so now here we cannot really use the data.size. Oof, okay. I don't think we even use this constructor. Let's make it explicit. Size. And I guess honestly I should actually change the block mapping as well. Because yes, I mean, since we are moving since we are moving towards like single dimensional arrays, it would be nice to have everything consistent. Right. And here. Oh, I guess this will be... Wait, was this size the... Setup checkers... Yes. Okay. Where was I? Right, okay, so this size goes away because I just simplified it. Okay. Yeah, unfortunately some of these are a little bit more awkward now, but I guess I have to live with that. Okay, the same here. Okay, and the same here. Right. And the same here. And the same here. Okay, let me just copy this. Probably that was the last instance, so yeah. Oh no, okay, here this and this. Yep, and yep. Okay, yeah, hopefully that's it. Let's try, and no, still problems. Okay. Oh yeah, I changed this constructor, but I didn't change the header. That totally is a valid complaint. Yep. Let's try again. Yeah, I'm kind of hoping this all works. Let's just rebuild everything. And let's just run the tests. So this one is fine, this one is fine, this one is fine, this one is fine. That should be actually it. Okay. So now we have the data in a single dimensional vector. So now we can make the state up thing. So what yeah, here. Okay, so let's just get this. And I guess just we can just return a copy. I mean, yeah, I mean that's what we want. Yes, okay. Okay, so now this gets tricky. Now we basically need some sort of support methods that will help us to figure out what actually changed. Because for each of these optimizations that I want to do, I kind of need to figure out like either which squares change, which rows, blocks, whatever changed. Okay. Actually, what's the... Yeah, I think it's a great time to actually take a short break. So yeah, I'm taking a short break. I will be back in like 5 minutes. Okay, and I'm back. Hopefully nothing broke in the meantime. Okay, so I guess I will introduce these methods one by one. So we definitely will need some methods that take the state and just give us some like distilled information out of it. But let's do it as we need it, because I'm not quite sure what methods I will actually need. Well, we'll see. Okay. Anyway, so let's go to the solver then. So in the solver, what we want to do for each of these for loops, instead of going over, basically instead of going through like either everything or all the changed blocks, what we want to do is have how to do this in a nice way. Right. Groups. Kind of thinking either creating a map, being basically string to state of the states, which has the benefit that I can just like name it as it is, so it could be like hidden groups 1 could be the state, right? Or I can just create variables for everything. The negative part of that is then I would have something like this, which is a bit awkward. Yeah, let's just do the variables for now. So now the question is, do we need... We don't need a different state for the hidden and naked groups, I don't think. So let's just call it groups 1. Sudoku state. Okay. So instead of looping over changed blocks, we said must trigger on every square change. Yes. So So we only care about numbers that were actually removed since last time. That's a thing we need to get over here. And I guess that's actually specific to each block. But otherwise, okay, so for hidden, and we care about all the change blocks. For the naked, right, we only care about squares where the change squares. Where the number of possibilities are lower than size, but in this case 1. Also, the set has to contain at least one change square. And actually, that yes, one change square that has this this property. That's what I wanted to say. Right. Yes. So these are actually different loops, I'm realizing. This will not be like this anymore. Interesting. Okay, so this one will be loop over changed blocks. Get numbers that were removed from this block and call solve hidden. Okay, so that's one. This one will be loop over also changed blocks. But then we want to do get a set of squares that's changed and where the number of possibilities is less than size, and so make it with the squares, right? And I guess if empty, then skip, right? Right, so if we have a block that doesn't have any squares that have changed in this particular way, then we just skip the block. We don't even trigger this. Okay. Okay. This actually needs to be after the block, because we make a change, then we want to remember the state. And then on the next iteration, we basically want to consider things or not. When do we actually want to save the state? No, we definitely want to save the state before, because if these methods actually are the ones generating the change, that's fine, and we want to consider those changes. Yeah, okay, so it's a little bit trickier. So we kind of want to consider so we always have the current state, right? And we want to look at the difference between the current state yeah, okay, so here why am I getting so confused on this? we want to look at the difference between which states. The current states, which is just Sudoku.state, that's the current state. And the state that we have stored before we applied the techniques in the previous loop, right? So yes, so these things we actually want to, yeah, okay, so the it's a little bit awkward. Okay, let me just get rid of this completely. So what we actually want to do is determine the change between old and current. Then I want to do old equals current, and then I want to apply the solving techniques. Right. So that basically means that this variable actually needs to be over here. And we need a special thing, so we need a way to get an empty state, because that's kind of what we are starting with. So this will be some sort of helper function. That I still need to write. So here what we do is I think I still want to bundle these two together, even though they actually do very different things. But I think that's fine. Yeah, so let's call it groups 1, or I guess I can make an array. Right, let's make an array of these. Oops. Groups. And we go up to the group of size, how much? I don't even remember. Yeah, group size 4, right? Shouldn't we go up to 5? No, because, yeah, okay. Groups up to group size 4, so in this case actually, yeah, 4. No. Yes. Ugh. And then groups 0, which will be size 1, empty state. Yeah, and I guess we'll be calling this for all of the sizes. So then here what I want to do is groups. Yeah, okay, so I need to figure out the change. So that's still a to-do. Once I have the change, I can do groups 0 equals sudoku.state. and then go for the solving. Right. Okay, this is starting to finally take shape, which is good. So, what do I need? I need the changed blocks. So that's one div. So this would be a std vector of unsigned. We don't have a good way to like refer to blocks, I don't think, right now, do we? Let me quickly check. Yeah, no, we don't. We just I guess, okay, this is actually not horrible. Just getting the blocks. That kind of works. Where was I here? Right. What's your problem? Because we already have a thing that's called changed blocks. Yeah, okay, we can put this into a subscope, that's fine. And I think actually I will not need these eventually, I hope. Yeah, it'll be kind of convenient to have it as an unordered set. So let's just keep that. Okay, so for the hidden, I definitely need the change blocks, that's fine. I will need a thing that, given a block and a state, it will give me the numbers that were removed. Right. So that's a functionality I need to add. So for a block and a and a state, return the numbers that changed. So this will be, yeah, I guess unordered set is okay. Remove the numbers. Then for this, okay, so we're still looping over the change blocks, that's fine. Get a set of squares that changed and where the number of possibilities is less than size. Okay, so I think for that one, yeah, we can just get the indexes of the squares, that's fine. Yeah, so I'm calling it interesting, it's basically satisfying this interesting squares is changed and number of possibilities is less than size of group. Right. Okay. So we need to write these two things, and then we need to adjust the solve hidden and solve naked to actually take this. And I'm already kind of seeing that this should actually be another method on the solver. that should be private. Solve groups. Well, at the minimum it will have the size as a parameter, and it for sure needs to have access to a state. State might just need a const x. Well, we'll see. Okay. Square. No, okay, so that's fine. What else do it? It needs to have an access to the puzzle itself, I'm pretty sure, and I guess the stats as well. Right. This might be good enough. Refactor, not refactor. Generate. No. What? How? This. Okay. So that will actually be this piece of code that I started writing up here. Basically, this thing will move to here, and I guess basically what I want to do here is just do solve groups of size 1 for this puzzle. Here have the stats. Yeah, okay, so this also should move down here. So group stats, and this will be groups 0. That's the state. Okay. So let's finish it then. Okay, so this one I want a method on the Sudoku puzzle that will give me the change blocks, but based on a given state. So this will take vector of squares, vector of squares, state. This will be a const method as well. Right. Do I have? Why is it putting into the? Okay. I ran into this weird behavior last time. It's like getting. Oops, no, this shouldn't be the solver. This should be the Sudoku puzzle. It's getting confused, and it's like putting things into the test for whatever reason, which is pretty strange. What? Oh, it didn't even fill the. Yeah, I think I have my project set up in some broken way because it's really getting confused. I really need to sit down and try to clear it up. Okay, so let's look at the other implementation of the changed blocks. Just go over all the pieces, has changed, and then yes, so basically the same thing, except we will not be calling has changed. what we will be doing is actually doing data is different than state I times size plus j. And actually quickly I need to check if our squares actually have comparison operator, because I'm actually not 100% sure about that. We have assignment. Oh, let's just search. Yes, and we compare data, that's okay. Right. So I guess this should straight up work. So we go over all our squares, we compare them against the state. If they're different, then we insert the blocks. Yep, okay. So that's a thing that should work. So change blocks, actually I can make it auto. Change blocks equals Sudoku dot get what? What's the problem? I mean, this isn't, is it private? No, it's public. Strange. Okay, just give me the change blocks from the state. That should be fine. For a block and a state, return the numbers that changed. Okay, so that will actually be happening in the loop. So yes, let's have a loop here. Basically this one. And I guess I can have them in one loop, that's okay. Yeah, I guess these two as well. Okay, so I go over all the changed blocks. Now this I want to get by block, so remove number, I guess this will be auto as well, because this will be Sudoku get removed numbers for a given block and a state. Yes. Yep. Okay, that I need to introduce. So I want to get an unordered set of indexes, remove numbers for a block. So this will be block checker. Oh hey, I don't know if starting from the first episode is the smartest idea. Just absolutely honestly. So one thing I want to do soon is actually make like basically guides for the code, because there's a lot of content already. Like each of the streams is like 3 to 4 hours, but you know, if you are into that, like go for it. Just FYI, the first episode has horrible sound quality. It got better over time, and I think this is my end setup that hopefully will stay around forever. But yeah, the first episode is pretty painful to listen to. So for a block and a state, I guess this can be const. State. Right. The block. Oh shoot. Okay, this gets tricky because I don't think I have a way to figure out index of a square from the square itself. Well, I kind of do, because I know they're just in a one-dimensional array. Well, this is an interesting problem. So, okay, our block checker. The block checker just has pointers to squares. Because this thing is a vector of square pointers. So this is a little bit awkward, but I can like from a square pointer I can definitely figure out which square it is because I know the pointer to the beginning of the array of the squares, so I can just, you know, do simple pointer mathematics and get the index. Actually, I guess like that means that I should. No, I cannot implement it in the block checker, can I? Phew. This will definitely have to access the LM. So it needs to have private access to this class. And like if Sudoku has private access to this class, I don't like that idea. That's very awkward. Because it's like basically the class that's kind of the parent of this class is like accessing it, and that's, to me, that sounds like a violation of encapsulation. But I don't quite like. I'm trying to think like what would be the helper method or function that I could just introduce. This gets quite tricky. Again, it goes back to the problem that I don't exactly know the square indexes. I could... Okay, so what I could do here... Well, okay, let's first of all, this shouldn't be implemented here. This should be implemented in the CPP file. That's one thing. Oops. So what I could do is I could pre-compute the indexes and give the state to the, or just give it a modified state. Okay. That's. I have a design idea. Okay, so what we do here is we go over the block. No, this still doesn't work. Damn it. Because to figure out like which squares this block is pointing to, I need to go over the private data member of the block. Ugh, annoying stuff. Okay. Yeah. Okay, so let's do it this way. I will just give it the base pointer to the beginning of the array. That's also like kind of violating the encapsulation because now the block checker kind of has an access to the entire state of the Sudoku puzzle, which is weird, but I don't know how to make it in a different way. I would have to basically like each square would have to be aware of its position within the puzzle, which also sounds like that would actually solve it, but it's weird. Like why? Yeah, I don't know. Okay, yeah, let's go back to the block checker. So here what we want to do is have the unordered map. No, set, yes, unordered set. Removed numbers, and this thing will get the state vector square. Well, definitely a const reference to this. Oops. And because I have to, I will give it the base pointer. So the base pointer is basically a pointer to the data of the vector that contains the squares. Based on that, since all the these pointers inside of this all point into the same array, I can then figure out basically the index of the square based on that. I'm not super happy with this, but I'm really not seeing a better way to implement this. Again, without actually introducing the knowledge of the index of the square into the square itself, which also sounds like very backwards and upside down to me, so meh. Okay, get the removed numbers from this block since the given state dump. Yep. State dump base pointer to Sudoku puzzle data used to determine the square index, right? And this is the set of removed numbers, right? So this thing will be implemented in the block checker CPP. Yep. So I want to go over my elements. Oops. Then how the heck do I do this? So this will be the offset index of the element. I minus base pointer. Then I basically want to do something like state minus minus I guess. Something like this. So basically I want to get the difference between the old state and the new state. And this is a supported operation on the square, so let me just find that quickly. Yes, here. Also, this is with a number, that's not our case, here with the square. Yeah, so we just do an AND with an inverse of the data, which removes all the bits that are not set. Removes all the bits that are actually set. So I guess now I just want to grab the remaining stuff out of the square. Yes. For that we can actually use the what was it? Next. Yes, next. So this method, what this does, it returns like the next number that's still possible, or if there isn't one, then it just returns a 0. So if you call it with a 0, then it basically gives you the first lowest number that's still possible in the square. And if there isn't one, like if there are no possibilities, then it just gives you a 0. Or if there is, like, if let's say, okay, let's say I have this kind of stuff and I call next with 6, then it also returns a 0 because there's like no higher number than 6 that's still possible in this square. Righto, so I can use this in here, and while next equals div next is different than 0. So we call the div next with the next and then store it back into next. So the first time it will just return the first possible number and then it will just keep iterating. So while this is not 0, which means that that's our end state, we want to start filling the result. And this will be result.insert next. Right. And state offset, right. This should be correct. Okay, it's pretty ugly code, but I guess that will work. So now in the smart solver, I will not be calling Sudoku, I will actually be calling block.removeNumbers. Oh shoot, no, I have to be calling Sudoku. Yeah, because okay, that's fine, because I need to get the base pointer. But this will just be return block removed numbers with the state and data.data, right? Yep, and actually let's just refactor, rename. Let's just call it consistently removed numbers everywhere. Okay. So okay, now I have the removed numbers. So this was for the hidden groups, right? Yes. So now I call block solve hidden groups with the removed numbers. because that's the big change. So now I need to go here, right, and I need another variant of this. Given size, filtered by removed numbers from the last time, from the last state. std set of unsigned removed numbers, right? And this thing needs to be implemented, block checker, right? So this goes here. So this will be very similar to hidden groups, right? This will be very similar to the other solve hidden groups. Here I need to return the result, of course. So I guess I can just copy the code, solve hidden groups, right? Right. So in this loop, instead of going over all the numbers, okay, how did I want to actually use it? I've already forgotten, and it has only been like what, 2 hours since well, less than that actually. So here we loop over the numbers. Has intersection. Out. Right, so basically here I think I want to do like kind of the same loop. Wait a second. No, I want to change the recursive find actually, not the... Yes, okay, so slightly differently. So I want to copy this thing actually and make a new one that will be recursive number find filtered squares and const std unordered set numbers, right? So only care about these numbers. Right. Yeah, so here what I want to do is I want to look up this number x plus 1u, and if it isn't in the set, no, sorry, if it is in the set, then I want to do found true, right? Okay. And then here, before I start like going over the elements, I can do if not found, then just return false. Yes. So what this does is okay, this function, so I guess this lambda gets called for every possible set of numbers, basically, of a given size, because that's what we do, like we call it with a given size always. And that's basically this function that does that. It basically tries like all, not permutations, because it's, I don't know what's the word for that, need to look it up at some point, but basically pick n out of a set, you know. So we are picking size number of elements out of a set. And this basically goes through like all the possible variants of that. And for each of those, it calls this lambda. So in this lambda, we are looking at a set of numbers. So if we don't have one of the removed numbers in this set, then, well, we already know that this cannot be a hidden group, because inherently, if this is the case, then we would have already found this group, hidden group, on like the previous loop. So we can just pop out of here, return false, and skip over this code basically. Yes, so recursive, where the heck is it? Solve hidden groups, yes. So this will be recursive find filtered, and this actually doesn't change then. This wants the numbers, so this will go here, right? Okay. So this we want to call in the solver. Okay, so this is fine now. Oh, I guess actually this will be over here. Now we kind of want to do the same idea with so this is basically done. Okay. So then for the naked groups, this will be very similar, just slightly different. So yeah, okay, so this is, we basically want the indexes of squares that should be part of the set, and then in a similar fashion where we were like looking that the number was in the removed numbers set, in this case we will come on to do the same thing, except we'll be looking for a square that's in the set of squares. And it will be the set of squares that had a number removed from them. Right. So this goes away. So here we will need some sort of call for interesting squares. Yeah, something like this. I guess that this would be just not interesting, changed. Block state, yes. Yes, that's the function we need. Okay, I need to take a quick break. It has been another hour. I need to refill my water and everything. See you in a couple of minutes. Okay, and I'm back. So let's implement the change squares method on our block checkers. So okay, I think this will need exactly the same interface as this. get the change squares from this block since the given state dump, base pointer, blah blah. Changed squares, right. This goes into here. Right. Okay. So this will be very similar to this, I think. So we are going over the elements. We calculate the offset, yes. Then basically what we want to do is not actually a diff, but if base pointer wait, what? Ah, yes. If state offset is different than I. Okay. Yeah. Offset. Wait, do I have a size here somewhere? Guess I could do element size, that's reasonable. Okay, take the offset. Just need to remember that these are zero based. I also need to add this into the Sudoku puzzle with exactly this interface. And this will go over here with exactly the same idea. Oh wait, this should be const. Did I not make it const in the header? I didn't. Okay, yes, this should definitely be const. Okay, and this is inside of Sudoku, and it's the same idea. So block change squares, state data dot data. Right. Ah yes. Okay, so that's fine. This can totally be const. Over here as well, and then in the header. Right. Okay, now it triggered, so I have the squares I'm interested in. So now again I need to make basically a copy of this function, which will be the modified one. So it will take the set, but not remove numbers. This will be the changed squares, and again I will be passing it into the recursive set find. Now I still need to add it to the header. Solved. This is this one, yes. Right. And I guess I can just copy this description. I guess I should be copying this description. Given size, yep, filtered by the changed squares. And what are you complaining about? Oh, this should be const, yes. Okay, no, it's okay. Just took it a while to kind of pick up on the changes. Okay, so this thing needs to go into the recursive set find. So, yep, I need another version of this. With this in here. Right. Okay, so this is a bit tricky because actually once we are inside of this function or this lambda, it's already too late. Because I don't think we will be helping ourselves too much with doing that. Oh, okay. I will just put it here, but I think actually this might make the code slower, honestly. Yeah, I might just get rid of this. I don't know. Actually, this... Okay, the condition that the number of possibilities within a square needs to be lower than size. That's actually important. Okay, now I actually am not sure if this set is zero based or not. Okay, it is zero based, yes. So that's fine, but did I actually break the recursive number find then? This one. Oh no, okay, because I do x plus 1. Okay, so that's fine. And I said this one is 0 based as well, so it just contains x. That's fine. Oh yes, this needs to come here by reference. So change square contains x, then found equals true. And I guess if lm's x dot count possible is bigger than size, then just straight up return false. And I guess I should do that before I check the found. If not found, then return false. Okay. I must admit that I'm not too convinced that this will actually make the code faster. It actually might make it slower. But that's fine. Like we can just write this and then test it exactly how it behaves. I think this specific check will definitely make the code faster. I'm not too convinced about this, because this is actually a pretty complicated operation. Okay, so I guess that's it then. So here we just do interesting squares, and again size not 1. Right, after we have applied the solving methods, we can update our state. So state equals Sudoku state, right? And oh, actually, yes, the main optimization that I wanted to do was actually if interesting squares size is 0, then I don't want to do this at all. Right, that was the main benefit of doing this. Okay. And actually I should do the same thing here, right? Because if we don't have any removed numbers, well, then what's the point of doing this at all? Let's change. I don't think I want to do it like this. Yeah, I think I want to do no. Ugh. Yeah, that I want to check just before I update the state, yes. Yeah, so I will need to introduce the method, that's fine, and groups of size plus, right. And then I need the hasChange state method. Where is the hasChange basic one? Right, okay. So has change, and we get the state, which is just a vector of squares. Oops, square. And we just need a const reference to that. True if a square was changed since compared to the given state. Right. Return square in the puzzle based on the given previous state. Right. And then I need to implement this. So this will be exactly the same, but I will not be calling has changed. I will be doing is different from state I times size plus j, and okay, this needs to be part of Sudoku, right? Okay, come on, wake up. Yep. Okay, so then in the solver, this should be now fine. Yes, it is. Okay. So now we can switch over to this one. So I just take this. Well, I don't really need that. Okay. In here, right? So. Okay, fine. So that we already have. Then solve groups for size 2. That's this thing. Solve groups for size 3 is here. Size 4 is here, and that should be it for the groups. Yes. Okay. I minus space pointer. Warning: conversion to CEST from long int. Right, because this can be negative, but not in this case, because I is always after the base pointer. So this is actually fine. Static cast. Actually, why is size T? Oh, because I only use it here. Wait a second, but. Oh, status. Oh, yeah, that's okay. Static cast size T. Okay. I minus base pointer. The same idea. Static cast size T. No operator. Oh yes, okay. Wait a second. I didn't make this const. No, this is const. So why is this complaining? Oh, because I only have equals, I don't have not equals. Yes, okay. Obviously. I guess I should rewrite it in a logical manner, but I'm too lazy for that. Yes, I need the empty state thing. So an empty state should be vector. Okay, I guess I will need size of size times size of Sudoku square size, I think. Just like, oh, this belongs here, not there. Damn it. Right, like this. Almost. Now it should be fine. Yes, because if I do Sudoku square size, it will initialize it with all possibilities present, which is exactly what I want. Yes. Too few arguments. Okay, so this would be Sudoku size, right? Sure. So this square test, Sudoku tests. Okay, these are still passing. Block checker, I don't think they should have actually changed at all. Solver. Okay, something broke. Okay, so we can no longer solve this puzzle. Okay, what did we break? I guess I should just write some tests for the new methods I just introduced. Yeah, possibly. Because a lot of those can be broken right now. Let's go into the block checker then. Actually, let's first do some hell of a test for the state thing. Okay, let's just grab let's just grab some Sudoku. Yeah, so this is like all the 4s are removed and then we reintroduce them, sure. So, okay. Well, okay, let's make it easier on ourselves. So first of all, auto state equals test.state. Now let's just loop over everything. Now if, or I guess one more, this will be the numbers. Okay, so now the state I times 9 plus j dot count possible should be 8. Not like that, I want this. And equals not a sign. So that's one thing. Oops, that actually should be here. Then if k is 4, then what we want is require not state I times 9 plus j dot is possible. Okay, otherwise we want it to be possible. Okay, so this is the Sudoku tests, right? Okay, so the state is fine. That's good. Now we can start playing with it. So what were the methods we introduced? Let's quickly go over it. We have right, changed blocks. We want to test the following methods. Changed blocks, removed numbers, changed squares, yes. Is that it? Might be it. Oh, I guess has changed also, sure. Okay. Right. So since we have a state, what you can do is change something in the puzzle. Let's just do 0, 0 dot I guess minus equals, I don't know, 3. Remove the 3. So now first of all we want the has change test dot has change with the state. This should be definitely returning true. Okay, let's see. Yep. And I guess before we do that, that should be returning false. Yep. So okay, change blocks, change numbers, right? So first let's do changed blocks. We have changed one number. Test.change blocks with state. So first of all, this should have affected 3 blocks. Okay. Yep. Okay, I'm getting suspicious about these passing tests, so let's just try to... Yeah, okay, so no, everything is working fine. Okay, so this works, I guess. Can we somehow verify that the blocks are actually the correct blocks? That gets tricky. Like, we would have to check the content of the block. Yeah, okay, like for the test, it would be so convenient to have some sort of ID for everything. I could like inject IDs in debug mode. That would be possible, I think. Yeah. Let's see. Okay. So if I now auto block blocks, if I just iterate over the blocks. So if I call remove numbers, test remove numbers on the block with the state. So first of all, this thing should be set.size equals 1 and set.begin the reference should be number 3, right? Or I guess 2? What does it actually return? It returns 3, okay. Oh shoot, are we actually using it wrong? Oh, I think that's the problem, we are using it wrong in the solver. But let's just finish these tests. So yeah, like all of those should report that there's one change number, well, sorry, one remove number, and that's the number 3 that we removed. I guess... Yeah, I guess I could test it further, but I mean, okay, I think this is good enough for now. But I still want to test this. Okay, so auto squares, change squares. Test squares block state. So this should report that the square at index 0 was changed. Require squares dot size equals 1 and squares begin. The reference should be 0. Okay, let's see. Yes, okay. So the only thing is, I think I'm using this set wrong in the solver. So the solve groups, right? So I get to remove numbers, solve hidden groups, recursive remove numbers. Numbers contains x plus 1. No, that's okay. Okay. Yeah, this is correct. So it looks like these methods all work fine. So did I screw up something in the solve itself? How do I test that? Oh, I guess actually, so it's this one that's failing, right? Yes. Okay, so I guess what I can do in here, oops, I can just yeah, what I want to do here is like a single step not solve. Yeah, basically call this method. So I can call it on one, that's fine. The puzzle is test. Why am I calling it test3? That's silly. Solve stats, sure. Stats. And I guess this goes away. And the state. Okay, so I want to start with an empty state. So again, that will be std vector of Sudoku square state, which will be 9 times 9, and Sudoku square of size 9. So this goes here. What are you complaining about? Like this. Yes. As a private member of Smart Solver, I know. Oh, that's so annoying. Well, okay, for the sake of argument, let's just make it not private. Which actually might be the correct way to go. Anyway. Oh, yeah. So, okay, if I solve let's see, if I solve it for size 1, then for this particular square, let's just test this one single square. So test 0 row 1 is possible. So 4 shouldn't be possible. 3 shouldn't be possible. So that's from the row. From the column, 6 and 2 shouldn't be possible. That's from the column. And from the square, 5, 6. Okay, so 5 shouldn't be possible. And the rest should be possible. So this should be true. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8, 9 should be possible. Right, let's see if this passes. Interesting. So yes, there's definitely something broken in the solve group. Okay, what's the time? Sure, well, let's go for a little bit longer. I wonder, is this? Let's quickly jump to the catch framework. Reference. What? Assertion macros. Okay. Okay, so I actually want to check in this case. Not require. Because I want to see all the things that are wrong. Five, 6. Oh, that's very interesting. That's screwed up in a very interesting way. So somehow we didn't remove the 2. We didn't remove the 5. We didn't remove the 6. We removed the 4 and 3. So it's correctly removing on the row. It's not removing on the column or the block. But somehow we removed the 8? How would that happen? Oh, because I'm blind. Okay, 8 should be removed definitely. Yes. Okay, so that's my mistake. But yes, okay, so it would seem that this is only propagating on the row because it removed the 3, the 4, and the 8. Yes, which is 4, 8, 3. Yes, so it only did the row somehow. Okay. Interesting. Okay, quick break. I need to grab a snack with a bit of sugar into my blood. See you in 5 minutes. Okay, and I'm back. So at this point, this is a perfect opportunity to actually use the debugger. So let's get the break here and let's look what the heck is happening here. Right, so change blocks. I really want to see what... Okay, this looks promising because... So this is saying... 25. Okay, this is a little bit weird. Maybe let me go back to the puzzle. No, this one, right? So okay, this row should be changed. 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 This, and this. So all the rows should be changed because they have singles in them. Columns. This one is changed, changed. Okay, so this one, the middle column isn't changed. Otherwise, all the columns are changed. And then let's look at the squares and... Okay, so this should be 26. Yes, okay, so it actually is 26 because only one of the blocks wasn't changed. Okay. And just looking at the pointers, I don't see any duplicates, so I think that's all correct. So okay, so the changed blocks are correct. That's good. So then I go over the changed blocks, right? So sure. Removed numbers. So what the heck just happened? Okay, that was a little bit weird. What? I mean, technically this block should be the... Well, okay, to be fair, I'm not sure which block this one is, but this looks weird. Like, this is not possible. Like, we cannot have a... Can we? No, we can have a block that has all the numbers removed because it's not like all the numbers are removed from all the squares. We are saying that these numbers were removed at least from one of the squares. Wow. But I mean, looking at the... no, okay, so this does make perfect sense actually. Let me just quickly grab this. Switch to programmer. Okay, so 511, that's just an empty square. Okay. 64. No, what the heck? 64. So 64 is 9, I guess. Yes. Then we have 4. Yes, okay, so this actually does make sense. So we have two singles that were set, and those both contribute basically the complement, so everything changed. Okay, actually, okay, so let's see what happens here. So now we solved the hidden groups. This shouldn't have any hidden groups because they're just two singles, so nothing should have happened. Yeah, okay. So what do we get for the interesting squares? Okay, why does this keep stepping in? That's weird. Interesting squares is 5 and 3. Does that match up with the elements? So 5, yeah, that's the one with the 4, and 3 is the one with the 9, I expect, yes. Okay, so this one should make a lot of change now. What the heck just happened? Okay, let's see. 4. Where's my... What the heck? Did I close the calculator? I think I did. Okay. If I check the 443. Okay, that's weird. Yeah, this like removed the wrong numbers. So the 4 is correct. Okay, let's go back to the 4. Yeah, so the 4 is correct. Yeah, I mean, so if I do bitwise OR with 4 equals, yeah, so that's fine. So if I do bitwise OR with 64, oh no, that still works. Okay, so it's actually correct. Okay. So wait, so this thing actually did the correct thing. So what the heck is the problem? I mean, at least it did the correct thing for this group. Oh, is this again the situation where I'm trampling over my own state? Because I keep asking the Sudoku removed numbers for a block and a state, but I keep looping and changing things. So should I just... Could that be it? It shouldn't really. Actually, if I go back to the puzzle, which block is this? So again, the 64 was, so that's 1, 2, 3, 4, 5, 6, 7. So a 7 and 1, 2, 3 and a 3, 7 and a 3. Where's, okay, so it's this row. I mean, the problem is this all looks correct. I'm not quite sure what's the problem. Remove numbers. Okay, what block are we looking at right now? We have a 2 and a 7 and a 4. A 3. 2, 3, 7. Where's my puzzle? Puzzle is here. 2, 3, 7. Okay, so it's this square. Okay. And this one is already the one that has the 7 and 3 removed. Yes. The thing that we keep changing the state under ourselves for the groups shouldn't matter, I think. It would be definitely cleaner to do it like make basically a copy of the puzzle, then make the changes and then swap it around. But I don't really see a reason why this would break. So, okay, so shouldn't really stuff shouldn't really happen. So do I still, yeah, okay. I mean, this again looks like it did the correct thing. So where the heck does this break down? Huh. I don't get it. I mean, let's just do... So we have just now seen that this one gets correctly calculated, right? So let's just check if it's the correct value. So this would be 8, 0, 1, 2, 3, 4, 8, 4. So 3 and 7 should not be possible. Two should not be possible, and that's it. Otherwise, everything else should be possible. Quite interesting. Starting to suspect that this is again some very stupid mistake. Because that's usually what happens when like things look correct, but somehow stuff is not working. Okay, let's see. So yeah, okay, so though it's really just on the first row. What the heck? This looks like weird off by 1 error or something. Or maybe we somehow mislabeled the blocks? I mean, okay, so there's one block that should not be processed. That's this one column. Everything else should be in the change blocks. Okay, so the problem is with a 2, a 5 and a 6. So the 2 is coming from the column, 5 and a 6 are coming from this block. Okay, let's try to get to a point where this thing actually I removed the yeah, I removed the breakpoints. Right, let's do this. what I want to do is create which point right now. Okay, this thing. So Sudoku get what was the method? There's like a yeah, no, not get change blocks. Get okay, so this thing, get call blocks, right? So new watch Sudoku dot get call blocks. Yeah, doesn't like this bastard. Can you just do it like this? No. Oh, it's not Sudoku. Damn it. What is it? No, it is Sudoku. Couldn't. Why the heck? If I do this, okay, so this actually is fine, cool. So, okay, so I know that I'm looking for this one. Change blocks. 3A5F0. Oh, it's the last one. Okay. Can I make conditional breakpoints here? Cool. Okay. So block equals this, and let's just do hit continue. Okay, so at this point block should be the column we care about. Yes, it is. Okay, perfect. So okay, let's see if things are making sense and if we are actually where we should be. So 371, so this is without the 3, without the 4, 5, 6, 7, 8, without the 8. Let me quickly go to the puzzle, and I think it is this one. So it is without the 3, 4, and an 8. Yes, so that makes sense. Then this one should be 484, so it should be missing 484. 1 and a 2, a 4. Oh, that's interesting. That is actually interesting, because the 371 wasn't missing a 4, right? No, it was. What? So did the block actually get correctly applied? No, but it's not missing a 5 and a 6. Okay, so that would actually mean that there's something broken with the blocks. Which is quite interesting. Okay, so then the 32, that's a 6, right? Yeah, 1, 2, 3, 4, 5, 6, yes. 507. Yeah, okay, I'm definitely in the correct place. Okay. So let's go back to here, right? So let's try to step over this. And okay. So at this point, what did we end up with? So the 371. Yeah, okay, somehow this didn't get... Let's go... So the 2 should be removed at this point. That did not work. Okay. I guess remove numbers is uninteresting, but what was... Where did the interesting squares disappear, damn it? What am I looking for? This, right. Why is it not here as a watch? Interesting squares. What the heck? Okay, that's definitely wrong. So it's the change squares that's somehow broken. What the heck? Okay, I think I will leave this as a mystery for tomorrow, because this will be some stupid mistake in here, I'm sure. Yeah, like definitely there will be something very silly in here that I'm not getting at this point. But actually, I have this thing. Okay, let's just try one more thing before I go. Okay, I just want to step through the change squares once. So let's stop this. Let's just run it again. So what we are interested in is the second column. So let's copy the value and let's make this conditional. Block equals this. Press continue. Okay. So now what I want to do is go here, and specifically let's just make breakpoints here, and let's just continue, and now we are here. Okay. Right, so just sanity checking. Yes, okay, this does look like it's the correct block, yes. So and the state is, yep. Yeah, so the state is just like all of them are empty. So that's good. So literally this thing should trigger on every square in this block, I think, because we don't have any. Do we have any 511s anymore? I don't think so. Yeah, so literally all of the indexes should end up in the result. So let's see. So oh, damn it. Okay. So offset is 1, which makes sense because I'm looking at the first element of the column. Oh, I already see what's the problem. Oh. Damn it. That's so annoying. Yeah, this is only correct for rows. Because if you are going in a column, this will be always the same number. It will be the index of the column. How do I get the position in the block of this? Ugh, that's annoying. Oh, actually super easily, right? So what I actually want is I just basically broke it by being too smart on myself. Okay, yeah, so this goes away. Okay, yep. And the thing that needs to change is this, so this will be lm at I, and this will just be I, because I care about the position inside of the block. I don't give a crap about the what's the actual index of the elements. Yeah. Okay, I still need this. That's definitely true, because I need to grab the correct thing out of the state. Yes, okay. Well, okay, so now interesting. Now we fixed the one test, but the second test is still failing. Well, that's quite interesting for sure. Okay, I just want to try this. Let's see. No. Oh yeah. And I just want to see if it's completely broken or what's happening. Like, what could have definitely happened is I made the... Yeah, it could be that now the solver doesn't trigger enough, and because of that it doesn't solve this puzzle. which is a different type of failure than like the solving is broken. So for this I would and it gets a little bit tricky. I'm not quite sure how to fix that kind of situation actually. Oh, I see a problem for sure. Okay, that definitely could be the source of my issues. Solver tests. No, it wasn't. Okay. It's like there's hope, but then there isn't hope. Okay. Yeah, this looks like it's kind of broken. Let's just try the top 10,000. Yeah, there's something wrong. I think it's getting stuck somehow. Oh, no, it actually did things. Okay. Yeah, but weirdly enough, I'm getting the feeling that now it's not triggering enough. Which is weird thing to say. Because if I remember, I will have to like recheck the solvers, but I think on the previous version this doesn't look correct for sure. Like there should be some doubles and triples in here for like definitely. Yeah, I think it's the conditions are somehow broken for bigger sizes of groups. I mean, I guess, yeah, I should just leave this for tomorrow. Yeah, like, yeah, okay. For sure, this is the problem. We somehow broke the bigger groups. Not quite sure how, honestly. I mean... Oh crap, I know how. It's always something stupid. It's always something stupid. Well, okay, let's see. Let's see if this was actually it. Of course, it's. This is the problem. Oh, amazing. How much time did I just waste with this? Like 45 minutes at least? Oh my god, it's always something completely stupid. No, I don't think it's still not working correctly. There's still something weird. I mean, at least the things are triggering correctly now, which wasn't happening before, but the stats are not reported, I think, somehow. Yeah, I mean, okay, at least this test is now passing. That's a good thing. I mean, okay, let's see if stats.groups at 1 is not 0. If it is, then things don't make sense. Yeah, so it's this particular puzzle actually does use the stats. So then I really I don't know what's happening. Yeah, okay, tomorrow. Ugh. Otherwise my brain will melt. Okay, so thanks a lot for watching. If you stay through, if you're watching the recording, then congrats for getting through the recording. Like, these are super long and I have no idea why anyone would watch the entire thing, but great, thanks. And yeah, I will be back tomorrow at the same time, 14:30 Central European time, as I do every weekend. So yeah, see you there, or you know, in another recording if you're watching the recordings. Bye.